thought we'd spend some time with implicit differentiation. So, most of your work in calculus, you're going to work with functions, right? Where everything is defined as y equals. But many times you can have things that aren't functions where you need to still find those rate of change and the derivative. So, when you look at an equation where y is by itself on one side, everything else on the other side, we call that an implicitly defined function. Something like y equals the square root of 25 minus x squared. Now, we also could write implicit equations. And that's where x and y are kind of mixed up in the equation. Y is not isolated on one side. It can look very much more like something like this. However, we still need to take the derivative, and sometimes we take the derivative with respect to x, but as we're going to see later on with related rates, we're going to be taking the derivative maybe with respect to t, something like that. And so let's take a little bit of time to look at how do I take the derivative of something where y is not by itself? So we're going to take the derivative of x squared plus y squared equals 25. Now to do that, I'm going to take the derivative with respect to t. I'm sorry, with respect to x. So when we take the derivative of x squared, that's pretty easy. It's pretty normal, like we've been doing. That's 2x. Now, when you take the derivative with respect to y, you've got to think that y is some function of x. So when we take the derivative of it, the derivative of y squared is 2y. That's the outside function, right? Something being squared. So the derivative is 2 times that something. And then we take the derivative of the inside. Now, the derivative of y with respect to x, we write that as dy dx. And let that sink in just a little bit. We know y is some function of x. Might look something like that. So when we take the derivative of y squared, we've got to take the derivative of something squared, that's 2y, times the derivative of the inside function, the derivative of y there, which we write that as dy dx. And then, of course, the derivative of a constant, in this case 25, is 0. Now, we're going to do a few more examples like that because I don't want you to get hung up on, well, I don't understand every detail yet. That's okay. Just hang with me a little bit as we look at a few more examples. So here we have an equation of a circle. A circle, obviously not a function, doesn't pass the vertical line test. So let's write the equation of the circle first. And I'll just do a little reminder of your Algebra 2 days that a circle's equation looks something like that, where h and k are the center and r is the radius. So looking at the graph, you might pick that the center is right there. So the coordinates for that center are 3, -2. So I'm going to write h is 3 and k is -2. Now, based on that radius, I'm sorry, that center, you've got to count the radius. So I'm counting at 1, 2, 3, 4, 5 is my radius. And we could clean that up to be x minus 3 squared plus y plus 2 squared equals 25. Now, let's take the derivative, okay? Thinking of chain rules here. The derivative of x minus 3 squared would be 2 times x minus 3. And then the derivative of x with respect to x would be 1. Now we take the derivative of y plus 2 squared. The derivative would be 2 times y plus 2. And then the derivative of y would, with respect to x, would be dy dx. It's still chain rule. The difference is the derivative of the inside here is 1, and the derivative of the inside here is the derivative with respect to x. So that's the dy dx. And then derivative of 25 is 0. Now, using this equation, let's evaluate it at 0, 2. So think about where 0, 2 is. It's here. And so I would get 2 times 0 minus 3 plus 2 times 2 plus 2 dy dx equals 0. We can solve for that. So 2 times negative 3 would be negative 6 plus 2 plus 2 is 4 times 2 is 8. So I'm going to move the 6 over by adding 6. So I get 8 dy dx equals 6. So it looks like dy dx is going to be 3/4. Now, think about what that means for our tangent line. That means our tangent line has a slope of 3/4. Looking at that point there, we can go up 3, 1, 2, 3, and over 4, 1, 2, 3, 4. Grabbing my handy dandy little Sonic gift card here. I'm going to line those two up, and I'm going to draw a little tangent line right there. That's what we find that our tangent line, the slope of our tangent line. Now, before I do these others, I want to move this around, make it a little simpler. So I'm going to subtract this term here. Okay, and that leaves me with 2y plus 2 dy dx equals negative 2x minus 3. And then I'm going to divide by the 2y plus 2. So I've got negative 2x minus 3 over 2 times y plus 2. Now those 2's in front are going to cancel, but the negative doesn't. So be real careful with that. I've got negative x minus 3 over y plus 2. Now that's going to make it a little simpler as we work through these other points, okay? Because we can just plug it in. We don't have to solve. We've already done that work. So let's do a 3, 3 here. So x is 3 and y is 3. That means that dy dx equals negative 3 minus 3 over 3 plus 2. So on the top, 3 minus 3, I'm getting 0 over 5, which is 0. So think about where this is on a circle. 3, 3. 3, 3 is at the top of that circle, so we're getting a horizontal tangent line. That's why the slope is 0. Let's do 8, negative 2. I've got 8 minus 3 over negative 2 plus 2. Now on the top, I get negative 5, but what happens on the bottom? I get 0. When I get 0 on the bottom, that's an undefined slope. Okay, so let's look at where that's at on the circle. 8, negative 2. I'm going to go 8, negative 2 is here. The tangent line at this point is vertical. That's why my slope is undefined. Making sense, right? Seeing the connections visually with those slopes. Let's do a few more. I've got 3, negative 7. That means dy dx equals negative 3 minus 3 over negative 7 plus 2. So 3 minus 3 gives me 0 on top, and I've got negative 5 on the bottom. So now I've got 0 over negative 5, which is 0. Remember back from this one up here, that becomes a horizontal tangent. So on my graph, look for 3, negative 7. There's my horizontal tangent line. All right, let's finish up a couple of more of these. So 6, 2. Now I've got negative 6 minus 3 over 2 plus 2. So 6 minus 3 is 3. Put a negative on it. Gives me negative 3/4. And 6, 2, 6, 2. So I've got my negative 3/4. Grabbing my handy dandy Sonic gift card. Down 3 and right 4. Line up that gift card there, that straight edge for my tangent line. All right, friends, 2 more to go. This one we're putting in negative 2, negative 2. So I've got negative 2 minus 3, and then I've got negative 2 plus 2. So negative 2 minus 3 is negative 5. Change the sign to the opposite, gives me positive 5 on top. And I get 0 again on the bottom. Remember, that's an undefined slope. That means I'm getting a vertical tangent at negative 2, negative 2. Vertical tangent there. All right, one more. 6, negative 6. So dy dx equals negative 6 minus 3, and then negative 6 plus 2. So I've got 6 minus 3 is 3. Put a negative on that. Then I've got negative 6 plus 2 is negative 4. So we get 3/4. Okay, let's draw that one. 6, negative 6, 6, negative 6 is here. And we're doing a slope of 3/4. So that's 1, 2, 3 up. 1, 2, 3, 4. And then, whoops. And then we use our straight edge to draw that tangent line. Okay, I think the visual really helps us to confirm exactly why we're getting these different derivatives and slopes when we move around something that's not a function. All right, so let's just do some practice here with finding dy dx. Remember, anytime we take the derivative with something with a y in there, it's got to have a dy dx in there. So when we take the derivative of y squared, I get 2y times dy dx. Then the derivative of 2x is 2. And the derivative of 3y would be 3 times dy dx. Now, once you're at this step, you've taken the derivative. Now you need to get all the dy dx's on one side. So I'm going to subtract this 3 dy dx from both sides. Now, friends, we cannot subtract those two. They're not like terms. One of them has a y, the other doesn't. So what we get to do is to write them side by side. Next step, notice that both of these terms have a dy dx, so we're going to factor it out like a GCF. So I'm going to take the dy dx, pull it in front, and then I'm left with a 2y minus a 3. If that was not clear, I want you to think about if you distributed it back to this parentheses, you would get these two terms. And our last step is to get this dy dx by itself, we've got to divide by this parentheses. So that gives me dy dx equals 2 over 2y minus 3. So that's how you can take your derivative, get your dy dx's all on one side, factor out a dy dx, and then divide by that parentheses. Those steps are going to be the same in each one of these. Now, each one of them is going to present a little bit different kind of equation, but I want you to see the process is the same. So let's look at the next one here. The derivative of 2x is 2. The derivative of e to the y is e to the y. We know that derivative rule already, but we got to take the derivative of the y, so that's a dy dx. Now, the derivative of x squared is 2x. And the derivative of y squared is 2y. And again, we're multiplying by that dy dx. Now, let's get all the dy dx's on one side, but also we're going to move the 2 to the other side so that the only things we have on the left are terms that have dy dx with them. So I'm going to add a 2y dy dx. And I'm also going to subtract a 2. Now, I know I can't subtract 2x minus 2. So like before, we get to write them side by side. So I've got an e to the y dy dx plus 2y dy dx. And then over here on the right, I've got a 2x minus 2. Okay, remember our step from before? Once we've got all the dy dx's on one side, we're going to factor it out just like it were a GCF, a greatest common factor. And that gives me e to the y plus 2y equals 2x minus 2. And then get to divide by that parentheses one more time. Now this one's super close to being able to cancel those 2's. I can't quite do it because that e to the y did not have a 2 with it. So I can't do that. So I've got to leave it like this. All right. Now my next two present issues with opportunities to practice with product rule inside of this implicit. So you might want to make yourself a note here that these are great examples for how do I do this implicit with product rule. Okay, so the first one, you see the product rule that's going to be necessary on the left. I want you to take the 2 with the x. So think of 2x as being the first function or first, and then I want you to think of y by itself as the second. So when we do product rule, that's first times derivative of the second. We know derivative of y is the dy dx plus the second, which is the y, times the derivative of the first. So the times the derivative of 2x, which is 2. Now let's take the derivative of the other side. The derivative of 3y squared is 6y times dy dx. We're getting in the habit there of putting that every time we take the derivative of a y, plus the derivative of 2x, which is 2. All right, let's move them around, right? We're going to move the 6y dy dx to the left. That will leave us with 2x minus, 2x dy dx minus 6y dy dx. And then on the right, I'm going to have this 2. And then I'm going to subtract this 2y. Okay, let's factor out my dy dx. That gives me 2x minus 6y. And then let's divide by the parentheses. So that gives me 2 minus 2y on top, 2x minus 6y in the denominator. Now, all of these terms are divisible by 2, every last one of them. So as long as you divide every single one of them by 2, you can reduce. So that dy dx equals 1 minus y over x minus 3y. Now don't get cancel happy here and try to cancel those y's. Remember, they are joined by subtractions to the terms in front of them. You cannot cancel them. The only way it worked, remember, is we could do it to every single term. It was the only way we were allowed to cancel there. All right, one more to go. You guys are doing great. Let's take a look at the last one here. The derivative of 5x to the third, that is 15x squared. Derivative of 3 is 0. Yay. Equals derivative of 2y is 2 times dy dx. Oh, now be real careful with this product rule. And the reason we have to be careful is that minus sitting right there in front. So I got a minus, and I'm going to open a parentheses. Now remember, let's take the 3 with the x squared, and we'll leave the y as the second. So product rule says the first times the derivative of the second, which is the dy dx, plus the second, which is the y, times the derivative of the first. And the derivative of 3x squared is 6x. Now, I would encourage you to go ahead and distribute this minus before you start moving things around. Sometimes if we start skipping a whole bunch of steps, we tend to make mistakes. So if you find yourself making mistakes, slow down, don't skip as many steps, and you can avoid that. All right, now remember, got to have only the dy dx's on one side. So we've got a good start here, but this 6y has got to move. He's got to be added to the other side. Kind of feels awkward with the dy dx's being on the right side. If you don't like that, of course, you can rewrite them. Just flip it around so that these terms are on the right, on the left, if you like that. I try to challenge myself to get out of my comfort zone sometimes. I mean, I really do like my variables to be on the left, and but sometimes I do try to challenge myself to go through the uncomfortable part of having them on an opposite side. All right, so I factored out the dy dx with a GCF. Now I'm going to divide by this parentheses. I want you to be thinking ahead. Can we cancel? Because it looks like a lot of things are divisible by 3 here. And I hope you're thinking, no, we cannot, because of that 2 right there. Pesky 2. We couldn't divide and simplify. All right. So how are we feeling? Hope we're feeling better about these. Now, the next few problems you're going to see are, now, what do we do with that? What kinds of questions could we see on the AP exam that have to do with this implicit? So this one says, for what values of x will this curve have a horizontal tangent? Remember, horizontal tangent means derivative equals 0. We did that with the circle, remember? Every time we got a 0 in the numerator, we ended up with a horizontal tangent. So we're going to take the derivative, we're going to set it equal to 0. Going to have some fun with this one, so be careful. All right, derivative of x cubed, 3x squared. Derivative of y cubed, 3y squared dy dx. We're getting good at those. Okay, now derivative of 4xy. Take the 4x as the first, and the y being dy dx, plus the second times the derivative of the first. And of course, the derivative of 1 is 0. All right, next step, let's move this over here to the left, and I'll move the 3x squared to the right. So I've got 3y squared dy dx minus 4x dy dx equals 4y minus 3x squared. Okay, let's factor out the dy dx. 3y squared minus 4x. And then I'm going to divide by that parentheses. All right, now I want you to think about, we're asking when is the derivative equal to 0? So if I take my derivative and I set it equal to 0, which one is going to matter? That the numerator equals 0 or the denominator equals 0? Think about this being 0 over 1. It's going to be the numerator, right? So we're looking for where 4y minus 3x squared equals 0. So I'm going to move the 3x squared over by adding it. And that gives me 4y equals 3x squared. And then I'm going to divide by 4. And you may say, well, that doesn't really help me. But that's okay, right? Because here's what I want you to recognize. You have an equation with two variables. You have a second equation with two variables. So you can solve these together by doing substitution. So I'm going to use substitution. I'm going to substitute 3/4 x squared in for y here. That gives me x cubed plus 3/4 x squared cubed equals 4x times 3/4 x squared plus 1. Ugh, looks ugly, doesn't it? So I've got x cubed plus, let's cube it, it's 27/64 x to the 6th equals 3x cubed plus 1. Now, this is where you're going to get to use your calculator to find the solution here. Okay, so let's pick up our calculator here. Remember, we're going to put one side in y1 and we're going to put the other side in y2 and we're going to look for the intersection. So here in y1, I'm putting x cubed plus, and then I'm going to put parentheses around that 27/64, and we're doing x to the 6th. And then in y2, let's put 3x cubed plus 1. You might want to start with like a Zoom 6. I'm not sure what this window might look like. So a Zoom 6 is a pretty safe one to start with a lot of times. So there's our first one. And then our second one should be coming. There it is in red. And so I'm looking for that intersection right there, friends. So I'm going to do second trace. Option number 5 is what I'm looking for. And then enter 3 times. The x value is the answer we're looking for. And so it tells me that x equals negative 0.770. So remember, AP requires 3 decimal places for that. All right, we're going to just take our calculator away to give us a little bit more space. And we'll finish up here. It asks, in terms of y, describe the x values where the same curve would have a vertical tangent. So remember, if a horizontal tangent happened when the numerator was equal to 0, then that vertical tangent is going to happen where the denominator equals 0. So that would give me 3y squared minus 4x equals 0. So in terms of y, describe the values of x. So that means we're going to solve for x. Let me subtract this 3y squared to the other side. And then I'm going to divide by the negative 4. That's going to give me 3/4 y squared. That's where we're going to have all of the vertical tangents are going to happen when this x value is equal to 3/4 the y value squared. All right, to finish up this lesson on implicit, we need to do some second derivatives. That is what that notation right there means. We're going to take the derivative and then take it again. So let's start with the first derivative. The derivative of y squared gives me 2y times dy dx. Plus, the derivative of 2y would be 2 times dy dx. And then the derivative of 2x would be 2, and the derivative of 1 would be 0. So just like before, we've got to get dy dx by itself. They are, so let's factor it out. Just like a GCF, that'll give me 2y plus 2. And then we'll divide by that parentheses. Lucky for us, all of those numbers, our terms do divide by 2. So we're going to go ahead and reduce it to 1 over y plus 1. Now, to get the second derivative, we take the derivative again. I think it's easier here to rewrite this as y plus 1 to the negative 1. We'll do a little chain rule to simplify this derivative. So now that we're taking the derivative again, we get the second derivative and we take it derivative here, chain rule, negative 1 coming in front, y plus 1 to the negative 2, and then times the derivative of the y, dy dx. Now, friends, what was dy dx in this problem? It was y plus 1 to the negative 1. We've got to make that substitution now. See, we can't just leave, say, second derivative is this times the first derivative, right? We've got to substitute the first derivative back in. Now, we'll add those exponents there. And then rewrite it with positive exponents. Looks like my second derivative is negative 1 over y plus 1 cubed. That's the extra step. That's the big got to remember for this particular concept. All right, let's do one last one. We've got a circle here, x squared plus y squared equals 1. The derivative is 2x plus the derivative of y squared is 2y times dy dx. And the derivative of 1 is 0. Let's move the 2x over, right? Get the dy dx by itself. Notice I had to subtract the 2x. And then let's divide by the 2y. So my dy dx actually simplifies to negative x over y. That's important. Okay, now let's do second derivative. So second derivative is going to require quotient rule. So I got low is y, d high is negative 1, minus high, that's my negative x, d low, that's my dy dx, all over low squared. Now let's go ahead and substitute in the negative x over y for dy dx. I've got negative y plus x times negative x over y all over y squared. Now, friends, I don't like that that fraction being on top. So watch what I'm going to do. I'm going to multiply every term in this fraction by that denominator. So watch, I'm going to multiply this by y. I'm going to multiply this by y. And I'm going to multiply this by y. You may be saying, well, why did you do that? Let me show you. Look what happens when I multiply that. Negative y times y, negative y squared, plus, I got x times negative x times y. But look, I've got it dividing by a y, so these y's actually cancel. It becomes negative x squared. And then on the bottom, I've got y cubed. Don't let the algebra here trip you up, okay? The calculus part you can do, but that's simplifying. Sometimes that trips up students, and I don't want it to get you. But hopefully, this helped with the implicit differentiation, both with first derivative and second derivative, because you're going to need these when you work with related rates. Feel free to leave me a comment there if you'd like to see something else. Feel free to like and share. Appreciate you watching. Bye for now.